Hello everyone. So today we're going to be talking about dynamic programming, and I know Professor Darden provided an introduction to this in the lecture on algorithm families. Today we're going to talk about it in more detail, starting with, we've got a picture here of a man named Richard Bellman. And Richard Bellman was the person who created dynamic programming. And he used to work for a government think tank that got a lot of its funding from the military, not surprisingly. And I believe it was, I've got a note here, it was the Secretary of Defense. It says he actually had a pathological fear and hatred of the word research. I'm not using the term lightly, I'm using it precisely. His face would suffuse, he would turn red, and he would get violent if people used the term research in his presence. So he was trying to get funding for research. He said he didn't even know what would happen if he used the word mathematical in this guy's presence. So he had to get funding for this mathematical research. But to do so, he couldn't use the word research. So he came up with the term dynamic programming for what he was doing. And he chose the term because, well, the word dynamic has no bad connotations. It's always a positive word. And so he thought that would be a great word to use, dynamic. It sounds like you're really doing something. And rather than research, obviously can't use that word, he wanted to indicate that it was somehow what he was doing was forming a plan for solving problems, and so he used the word programming. So he stuck two words together just to make a good term that he knew would get him funded. So we're kind of stuck with this odd terminology, which now actually we often use for programming. So it's good in that respect, but the word dynamic doesn't really have a good feel for what we're actually doing here when we're doing dynamic programming. So the idea is that when we have a recursive algorithm to solve a large problem, it generally divides the problem into independent subproblems. Like if we're doing a tree traversal, we can do a traversal over the left tree and we can do a traversal over the right tree. Some problems, though, do not have independent subproblems. They have overlapping subproblems. They have repeated subproblems where the same subproblem occurs over and over again. And so we can use dynamic programming in this case when there is not independent subproblems. And when we use dynamic programming, we can write bottom-up solutions, we can write top-down solutions. For the problems that we would give you, generally you can write, if it is possible to write one, it is possible to write the other. I started to say you can because, sometimes just a given person sees the bottom up or sees the top down, and it may make the other one difficult. But if for the problems that we give you, both types of solutions are possible. There are a few problems where only one of them is really a possible solution, just because, like in a really complex problem, it may be hard to see what the base cases are, to see the starting point, like the best way to build a bottom up, and that I'll know when the absolute base case is when I get to the simplest possible thing, but seeing how to build it from the bottom up is sometimes difficult with really complex problems, but we won't be looking at any of those. When people ask, I always have to go find a list of DP problems for which only a top-down solution really exists. But if you want to, you can do that Google search and save me the time. So when we can use dynamic programming is when we have a large problem that can be broken down into smaller subproblems, and the subproblems are not independent. The same subproblems recur over the course of solving the larger problem, hopefully many times. We want these things to occur many times because that's what's going to save us time in the long run, is remembering the answers to these subproblems rather than recomputing them. So the goal here is to reduce the time to run a recursive function, and this does change the complexity class, and we will see how it does. So backtracking and branch and bound generally speed up the runtime, but we can't see whether or not it even changes the complexity class. It may just cut out enough that even a bad complexity class is doable. It may change the complexity class, but we don't know with backtracking and branch and bound. It's very hard to look at a specific problem and know if our pruning has changed the complexity class. It often does not. But here with DP, we are going to see that we are going to change the complexity class in many times very appreciable ways, changing from something like, it says c to the n, so changing from exponential time to polynomial time. And we're going to do this by using extra memory. We're going to say, hey, I'll say if I could use this much memory, a reasonable amount, I could save this much time, a huge amount of time. So the technique that dynamic programming uses is called memoization. Now, it has the same Latin root word as memorization, but memorization with an R implies that there is an intelligence there making a decision. With us, the intelligence goes into the coding. The code doesn't memorize things. The code memoizes things. The code just writes some values down. There's no intelligence involved. There's no AI involved in the algorithm. The intelligence is in building the algorithm. So dynamic programming uses memoization, and will often just say things like memo, the data that we wrote down for future use, when we refer to how we're doing dynamic programming. So what we do in memoization is oftentimes we can take an existing function that solves a problem that's amenable to DP, that has repeated subproblems and they're not independent. And what we're going to do is we're going to modify the function a little bit so that this function that used to maybe do brute force will then, when it's about to exit, it will save the inputs and the result. And then when the function starts, it will check to see, hey, do I already know the answer for this input? If I have, let's just retrieve it. Let's look it up in the memo and return it. And if not, then we have our code the way it was, except that before we exit, we save the value and the input. And in many cases, if it's possible to do this, it's possible to do it with minor code changes. So we're going to look at a couple of problems today, how they could be coded with and without DP, and see what the changes are. So a classic problem in memoization is Fibonacci sequence. The definition of the Fibonacci sequence is recursive. F of n equals f of n minus 1 plus f of n minus 2. So it's very easy to write a recursive definition, therefore it's easy to write a recursive function. And it's possible to write an iterative version of this without DP, but we're going to see some advantage in the DP approach in a little bit. So we can write a recursive definition. When we solve f of 3, we find that we need f of 2, f of 1, etc. As we do a larger, oops, I thought I had a blank slide in here. As we do a larger Fibonacci number, and as I remember Professor Darden mentioning it, let's just do f of 5. Let's do a small one, not like a huge one, just f of 5. F of 5 needs f of 4 and f of 3. Well, in f of 4, I need f of 3 and f of 2. In f of 3, I need f of 2 and f of 1. Okay, well, hey, I've got a base case there. I've finally gotten down to one base case. And f of 3 needs f of 2 and f of 1. F of 2, oh, we've still got 3 places that need f of 2, which need f of 1 and f of 0. So we computed f of 3 1, 2, 3 times. We computed f of 3 2 times. And so we're starting to see how the how saving these results could save us time, even in a small Fibonacci number like f of 5. The function here is a straightforward implementation of the recursive definition. If I have a base case, if I is 0 or I is 1, return I. So f of 0 is 0, f of 1 is 1. Anything else is recursive. And it seems like an innocent enough little function, but it has exponential runtime. And in fact, it has somewhat an interesting exponential runtime. Does anyone recognize that number, 1.618? So 1.618 is an approximation. It is, this value 1.618 is known as phi, which is equal to 1 plus the square root of 5. Oops, I didn't really need that parenthesis since I'm going to draw a line under it anyway. 1 plus the square root of 5 divided by 2. So that's phi. Phi comes up in lots of things. It comes up in ratios in classic architecture. It comes up in breeding rabbits. It comes up in the ratio of the areas of the subsequent shells of a nautilus shell, which is a marine organism. And so this number comes up a lot of times, and it comes up in Fibonacci numbers. It also happens to be, if I take the limit as n goes to infinity of f of n plus 1 over f of n, the ratio of successive Fibonacci numbers approaches phi. So it's a number that comes, oh wait, I'm going to pause here. Okay, I just got to pause on my preview. Okay, so this number comes up a lot in mathematics and nature, etc. And it also comes up in Fibonacci numbers. But it gives us an idea, this approximation 1.618, it gives us an idea of how inefficient this is. It's not as good as linear. Linear would be 1 to the n, but it's much, and it's a little bit better than 2 to the n. So it's much worse than 1 to the n. It's a bit better than 2 to the n. It's still exponential though. So if you write a program and tell it to compute like fib of 45, it may take a while, like on the order of a few seconds. And then as you go up, it very, very quickly ramps up after that. Like fib of 47 might take a minute on a modern computer. So this implementation works, but it's horrifyingly inefficient. Now, what we could do is, we've got a preview here. We've got a main function, and we've got a prototype for our fib function that's going to be on the next slide. And I said, hey, let's figure out first of all, what the maximum Fibonacci number is. That's the biggest Fibonacci number that fits in a uint 64. So the function says, I'm going to accept a uint 64. I'm only going to accept a uint 32. Actually, we could have accepted a uint 8 in this case. But in a 64-bit number, 93 is the biggest Fibonacci number we can represent in a 64-bit number. So we created that named constant, and we got our function prototype, and we said, hey, let's run through and print all of them. And so here is a dynamic programming version of this function. So the dynamic programming version says, I'm going to make an array, a static array, we'll come back to that. I'm going to make a static array of size max fib plus 1. So since I can do 0 through 93 inclusive, I need an array of size 94. And I initialize it with the list 0, 1. And it turns out when you do partial array initialization like this, G++, actually it's a C++ standard. All C++ compilers, when you do partial array initialization, if you give it at least one value, it will fill in zeros for anything that you don't specify. So we get basically 0, 1, and 92 zeros after that. So the function says if n is outside of the range of possible numbers, then just return 0. And I wouldn't even call that a base case. It's really just a safety mechanism. Okay, then the next one says if fib sub n is greater than 0 or it's equal to 0. So it's saying if I can look it up, in the array, or it's a base case. So this is basically this two-part if is catching base cases, n equals 0, n equals 1, and it's catching things we already know. So rather than having a base case and a look it up, I've combined the base case, the two base cases, and the I already know this value. If what's in the array is greater than 0, I already know it. And then if I do know it, I return it. If I don't know it, I compute it. This is the same code we had before, is compute it, make two recursive calls, but I don't just immediately return it, I save it in the array. And we could have actually written this last part all in one line. We could have said return fibs of n equals thing, and the assignment would have to happen before the return happened, but I didn't want to make it too cryptic. So we compute the new value, we store it into the array, and then we return the value we computed. So now what we want to do is let's look at the static. So that word static means something special. In the previous slide, we used static to make a thing that is global but is not a variable. So a const is something that doesn't change. Static basically means there's only one of this. And so it isn't a global variable because it's const, it's a global constant. So we've gotten around the bad things that happen with global variables. So we don't have a global variable, we've got a global constant, but the word static means something else. The word static means there is only one of this. When we use it inside of a class, remember, if I put static inside of a class, it means there is only one of this. There is only one of this regardless of how many objects are made. There is only one of this variable, and all of the class objects share this one class variable. So a static thing inside of a class isn't a member variable, it's a class variable. One of it exists for the entire class. And it exists even when the class doesn't have any objects. It retains its value even if there are no objects in existence. When we make it inside of a function, a static variable inside of a function means this variable always exists, it always maintains its value, even if the function is not running, this array does not go away and it doesn't lose its values. So the initialization here does not happen every time the function runs. That initialization happens at compile time. So this array gets initialized at compile time to contain 0, 1, followed by a bunch of zeros. Then after that, whether the function is running or not, that array still exists, and it maintains its values. So let's think about what happens when I call this function. Let's say I call it for the first time, and I compute, say, fib of 5. Well, it computes. It says, well, do I know fib of 5? No, it's not in there, right? So I say, hey, let's compute fib of 5. And it says, well, fib of 5 isn't in there. But look at the order of the recursive calls. The left one has to happen first. So it has to compute fib of 4 first. And until fib of 4 is done, it doesn't try to compute fib of 3. It doesn't try to add. It's got to compute this first. So fib of 4, we say, is this one in the array? Or is it a base case? No. Okay, well, we've got to compute it. To compute it, we need fib of 3. To compute fib of 3, we need fib of 2. Compute fib of 2, we need fib of 1. That's a base case. Oh, wait, I'm going to do a different color for this one because it's actually in the array already. It's a value that we pre-populated. So we need fib of 1 and fib of 0. Now we're done with fib of 2. We can go back to fib of 3. Fib of 3 needed fib of 2 and fib of 1, but that's already in the array. Fib of 4 needed fib of 3 and fib of 2, which is already in the array. Fib of 4 is now computed and stored. Fib of 5 can pick up where it left off. It called fib of 4. Now it calls fib of 3, which is already in the array. So that took how long? Took about O of n time, because it only computed values once. So this took about O of n time to compute n. So if I had started up my program, just run it from the command line and said I want fib of 5, it would have computed about 5 values. If I had started the program and asked for fib of 20, it would have computed about 20 values. Here's another question. What if I leave the program running and I just computed fib of 20, that took about 20 operations, and I ask it for fib of 20 again? It's already in the array. It's constant time. If I ask for fib of 21 is basically, well, I need fib of 20. Oh, I've already got that. I need fib of 19. I've already got that. That was basically constant time. The nice thing about this function is future calls to it. If the same program keeps doing different fibs, subsequent ones run faster because I've already computed some of the values. If I ask for fib of 40, well, it takes how much time? N over 2, because it's got to compute from fib of 40 down to fib of 20, which it already has. And it's done. So this one is really amortized complexity. This one is amortized complexity O of 1, because it depends on a sequence of events. A sequence of events, each one takes about let's say k was the biggest value we previously computed. It takes O of n minus k time, where k is the biggest value previously computed. But if the previously computed value is k or smaller, it takes constant time. So it basically takes amortized O of 1 time for many repeated calls. Most of them are constant time. So this is an advantage. We could write this function with just a for loop and fill the array up from the bottom up. So here's an example of a bottom up. So this one is bottom up. It says it's DP because we never compute values that we already have. We memorize them and we use them in future calculations. So I start out, I've got my array, I've got my I is the value I was given, and it says I is the minimum of I and max of n minus 1. So basically what that's saying is if they try to compute too big a value, just compute the biggest value we can. So this is a slight difference from the other one, which said, hey, if I can't compute the value, just say 0. This one says, well, if I can't compute the value, make it the biggest thing I can compute. So if you ask for fib of 100, you get like fib of 93. Okay, so not too bad. So this one then says, I know f of 0, I know f of 1. Let's put those in the array. And we didn't have to do it that way. We could have done it with the initialization syntax here. We just wanted to make it clear that we were doing things from the bottom up. So we computed f of 0, we computed f of 1, and then I can compute every k less than or equal to I. And I know, because I am filling in values starting at 2, I know when I get to a future value of k that what I want is already in there. Either k is 2, and I know 0 and 1 are already in there, or k is some larger value, and I know k minus 1 and k minus 2 have already been computed because I am computing from the bottom up. Now notice in both the top down and the bottom up. Top down and bottom up both compute the smallest values first. 0 and 1, not just 0 and 1, which are base cases, but look back here. F of 2 got computed before anything else did, and then f of 3, then f of 4, then f of 5. The values always get computed from bottom to top, regardless of how we write the code. So when we say top down, we are saying how is the code organized. When the code runs, it always computes the smallest values first because it has to. It says, well, I don't know fib of n, but let's try solving a smaller problem. Oh, I don't know the smaller problem, let's try a smaller one. And eventually it gets to a base case and it can build up. So top down versus bottom up is how we write the code. Behind the scenes, bottom up is how it gets computed, but top down versus bottom up is how we wrote it. So this one is written from bottom to top. It computes small values before it tries to compute big ones. Top down says, well, I'd like to compute a big one. Let's try to compute something a little bit smaller. Let's take a big problem and make it a little bit more manageable. Bottom up says, I know it's unmanageable. Let's start with the smallest things, the ones that are easy to compute, and build up to the bigger things. So this one saves all of the previous values in the array, but this one, every time you compute fib of n, this one takes O of n time. So this one is always O of n time. This one is amortized O of 1 time. Both of them take O of n memory. They both have to save the values that have been computed, and really you could say, well, isn't it a constant number? It's really the size of the biggest Fibonacci. Well, I could use a different computer. Maybe there's a G++ out there that supports 128-bit integers, and I could compute slightly bigger values. There are libraries that allow you to have arbitrary precision values. And if I had arbitrary precision values, then I couldn't pre-compute what's the biggest thing I could compute. So I'd have to have something else. And when we do the final exam review, we're going to give you an example of how to do this without knowing a maximum size up front. We didn't use one of the arbitrary precision libraries, but we did do this a different way. So if we can't have an array, right? I can't have an array if I don't know how big it has to be up front. I could use a vector and push back and let it grow. I could use something else. So think about what else you could use. So we've converted the exponential to either O of n or amortized O of 1. Now here's another example of a function that doesn't look too bad. Binomial coefficients. We say, hey, I want n choose m. So n choose m, if you haven't had statistics yet, that's okay. It's not required to understand this. And we're not going to ask you questions about like how this gets computed, but you should understand what it is. It's a problem that computes n choose m. N choose m is like, oh, I have, when I'm teaching in a normal semester, I have like maybe 5 different colors of dry erase markers that I can use, and I need to use 3 of them, for example, for a particular example. How many ways can I pick 3 colored markers out of 5 possible colors? So that's n choose m. And so the definition of this is n factorial divided by m factorial n minus m factorial. So it doesn't look recursive, right? It just looks like we need to compute some factorials, and we could do that recursively or iteratively. Oh, there's a problem for this. So our straightforward, let's just compute the factorials, overflows integers really, really quickly. So 13 factorial overflows a 32-bit integer. 21 factorial overflows a 64-bit integer. If we had a 128-bit computer, we'd still overflow it with 35 factorial, and we haven't even gotten to computing the Powerball odds with like 45 factorial. So it's not good to try to compute the binomial coefficients using factorials because they grow so rapidly. So you can say, well, I know I'm going to divide. Let's just do the cancellation all by hand and simplify the problem. Well, that's great, but I wanted to write code, and I don't want to write that code. So I don't want to write code to do simplification of ratios of factorials. I just want to write a program that will compute it. So, turns out binomial coefficients have a recursive definition. It has base cases. So the base cases say, I've got n colored markers, how many ways can I pick 0 of them? Well, there's only one way to pick 0 of them. Don't pick any. There's one way to pick none, and that's to pick none. Okay, I've got 5 colored markers. How many ways to pick all of them? There's one way to pick all of them. You pick all of them. So those are base cases. Then it says, well, n choose m is equal to, and you don't have to memorize this. We're not going to give you this problem on the exam, but it says there's a recursive definition. If you want n choose m, you take n minus 1 choose m minus 1 plus n minus 1 choose m. Trust us, it's the right formula. So you can go look it up, but we did get the formula right. So there's the recursive definition. So now this one you say, okay, this I can write. This I can code up, and it'll be able to solve, like the Powerball numbers without overflowing an integer. No problem. So we write it. We say, hey, if I've got a base case, if you want to know how many ways to pick 0 or how many ways to pick all, then return 1. Otherwise, return 2 recursive calls. Is it elegant? Yes, assuming that you're okay with recursive code. Is it efficient? No. It's exponential again. So it's exponential. This simple little function, return thing plus other thing, but those 2 recursive calls grow exponentially. So here is a top-down approach to solving it. So this one says, hey, I'm going to call my binomial helper. Let's look at the bottom code first. So I got binomial helper. We wrote that first. Let's look at the binomial function. Binomial function says, hey, I want to compute n choose m, some unsigned integers. I want to compute n choose m. Well, I'm going to do top down. So what I'm going to do is I'm going to create a memo, and then we even called it memo. So I'm going to create a memo, and I'm going to call my helper that knows how to do recursive work. And I'm going to basically set up the memo and call the solver, and when it's done, I return whatever it says. Okay, so I call the helper, I return whatever it says. The helper says I accept n and m. Notice we pass integers by value. Because we don't need to modify them, that's the most efficient way to pass them. Don't pass integers by const ref. Ooh, it looks like we've got a slight inconsistency here. We could have done a slightly better job. We used uint32t's here, should have used uint32t's there. Oops. They are, for most compilers, those are equivalent. But it's not guaranteed to be, but generally it is. But we shouldn't have written code that assumed it was. So we accept n and m by value, and we accept a memo by reference. By reference because we're going to change it. We're going to pass it to future calls, and we're going to look it up in subsequent calls. So we've got to have it passed by reference, not just for efficiency, but to make sure we can modify it and everybody sees the changes to the one and only memo. Okay, so in the function here, we've got our base case. It says, hey, if you wanted 0 or n, store 1 in there and return 1. So we populate the base case and we return it. And we could have said return memo of mn. Not a big deal. But we just returned 1 because we know it's the answer there. Oh, one other thing I forgot to mention is the m plus 1 and n plus 1. Because I want to be able to compute something like, let's say, 5 choose 3, well, I need to choose 0 through 3. 0, 1, 2, 3. So I need a size of 4. So that's why we have the plus 1 on both of these, is that we need the 0 value. It's the base case, but we need the m value. It's the thing we want. We need to store both of them, so we need size n plus 1. So this is something that we did in the Fibonacci, and I'm so used to it, I forgot to mention it. Oh, we got questions not getting answered, so yes, you can. We could use an unordered map. It would basically map the I, the number, to the Fibonacci. The I would be the key, the fib of I would be the value. Okay, so we've got n plus 1 here, m plus 1, and this is something that you have to look at individually with every DP problem. Do I need a memo of size n, or do I need a memo of size n plus 1? What am I computing and where am I storing it? So since it's convenient for us to put, picking 0 at index 0 and picking all of them at index all of them, we need plus 1 in our sizes here. Okay, so back to our base cases. So we say if it's choose 0 or choose n, store 1 in there and return it. If the value's already known, so if the value's already in there, then return what's in there. So that's the dynamic programming check. If I already know the answer to this one, return it. Otherwise, compute it with 2 recursive calls and then return what we just finished computing. So we've got our 2 recursive calls, and the only thing that's really changed about our recursive calls is the memo gets passed. The helper needs to be given the memo. So that's why we wrote this in 2 pieces with a base function and a helper function, is so that the base function could create the memo and give it to the helper. Could we have done this with a static vector or something like that? Ooh, problem. This one would be dangerous to do that way, because if we left the program running and the user got to say, well, I want 5 choose 3, I want 7 choose 6. Well, if the first time the function runs, it creates a vector of size 5 choose 3, the next time it would take complicated code to figure out that the vector needed to grow, not just that the vector needed to grow, but that the values in it might be wrong and might all have to be replaced. So with the fib, static was fine because the answers, even though we might need bigger and bigger values, the smaller ones never change. But here, it's possible that values could change because we've got bigger possibilities. So we want to make sure, and also the size would change here. So we want to make sure that we always had the right size memo and didn't have to figure out if it had to get bigger or what size it already was, etc. So it actually made the code simpler here to recreate the memo every time there's a new call to binomial. Okay, so we check if it's a base case, check if we already know it, and if we don't, we compute it, store it, and return what we computed. And so this one has complexity is a bit hard to see in this one, but think about our vector, right? We've got this vector of size m plus 1, n plus 1. So I've got some number of rows and some number of columns. I compute everything in there that's needed. Some of them won't be needed, right? There's if I'm saying I want to compute 10 choose 7, well, it's possible there's values I don't need, but it's hard to see them. But at most, I'm going to compute every value in here. I'm going to compute all m plus 1 of these. I'm going to compute all n plus 1 of these. Hey, that's basically O of n times m. So you can think of it as quadratic. It's also, it's linear in both sizes. So it's O of n times m. Now, oops. So this one is O of n times m, because I have to compute every value, possibly every value in there. But I'm never going to compute anything more than once, so it can't be any worse than n times m. Now, that's the top-down version. It just says, hey, you want to solve a big problem? Fine, I will solve smaller and smaller problems until I get to things that I've already computed or I get to base cases. So the complexity, it's hard to see what the recursive complexity is from it, but we know how big the memo is, we know how many values are in the memo, we know we're never going to compute anything in the memo more than once. Okay, this is the bottom-up function. And this one is harder to write. Professor Darden and I spent a little while making this one and getting it to be correct and doing as little work as possible and not computing things that weren't needed. And it still does compute some values that aren't actually needed. We tried making it even more complicated to cut out some of the things that were never used, and the code got significantly more complicated, and we decided you don't need that. So here in the binomial coefficients BU bottom up, it says, let's create the vector, same type of vector, same size. So we create the vector, and then we say, well, let's loop from I to is all the possible values of m. So I'm saying, hey, let's go through all the things I could pick, but for everything I could pick, let's go through every possible thing I could pick it out of. So if I'm picking 0, I want to pick 0 out of 0, pick 0 out of 1, pick 0 out of 2, etc. Because if you look at what we need here, the order of these tells me what order the loops has to be in. Basically, I'm going to compute things that are either the same I or smaller, but j is always going to be smaller. See, sometimes I is the same, sometimes I is smaller, but j is always smaller. So I has to be the outer loop. I can't have I be the inner loop because then I might get an I that I haven't computed yet. So j is going to be the inner loop, I is going to be the outer loop, and then we've got our base case. If I is equal to j or I is equal to 0, then it's 1. Otherwise, compute the value from smaller values in the vector, and then when we're all done, we return the very last thing in the vector. Now this one is, you can see from it that it's computing approximately half of the 2D vector. There's portions of it that don't get computed because they just don't make sense. But there's still O of n times n complexity. Now here's where the beauty of the top-down comes in. The top-down never computes something that won't be used. This one sometimes does. If you really think about it and look at the problem, you'll see there are values in here that aren't actually going to get used, but it's hard to see those. And like I said, when we made the other solution more complicated, it was harder to understand which ones exactly weren't needed, and the loop conditions became more complicated. Ifs became more complicated, and so it was a good exercise for us as professors, but we decided it was just too complicated for you. What we wanted you to see, though, is that, hey, if there are values that don't need to be computed, it might be hard to see those with bottom up, but top down just won't compute them. Let's do a simple one that's easy to see. So I've got, rather than fib, I've got function g. G of n is equal to g of n minus 2 plus g of n minus 4. And then we would have to have base cases, obviously, because we got to have at least 4 base cases, right? Because I want to compute g of 4, I've got to have g of 0, 1, 2, and 3 in order to compute g of 4. Or actually, yeah, g of 4 would go down to g of 2 and g of 0. So I can compute g of 4, but I would need g of 0, 1, 2, 3 to be base cases. Now, this one, you could pretty easily see that a top-down solution will, if I give it an even number, it computes even g's. If I give it an odd number, it computes odd g's. But I would actually have to put a little bit of effort into the bottom-up code to say, oh, you know what? My loops can skip by 2's. My loops don't have to start at like 4. They might be able to start at 5, right? If the initial number was odd, I can start at 5 and skip by 2's. If the initial number was even, I can start at 4 and skip by 2's. But I would have to work at building that into the bottom up. Whereas the top down, you give an even number, it only computes even g's. Because it only calls itself with even g's, it only computes even g's. So that's an example of how we would have to notice what was not needed and make the code more complicated to make the bottom up do the minimum amount of work. But the top down will always do the minimum. The bottom up might do the minimum, it might not. It depends on the problem, it depends on the code. So that's the binomial coefficient, the top down, the bottom up. Again, we're not going to test you on the code. What we want you to come out of this knowing is that binomial coefficient is hard. It's exponential. It can be done with DP. It can be done top down or bottom up. And the structure of the problem is what really is good to take away from this. In the bottom up, I didn't need a helper. I needed one function. I created the memo, I used it. When I'm done, the memo's done. But in the top down, I split it into two functions. One function to create the memo, one function to compute everything that's needed and return it, and then the main function returns the final value. So this is really good takeaway for future implementations of DP. For Lab 10 this week, we're going to have you implement a DP problem. And on the autograder, it has something kind of cool in the autograder. If you write your function and you just make it really, really simple, you make your function return negative 281 is the solution to the problem. The autograder in the run out, like if you click on the timestamp, it'll give you a bunch of help. Now, what I would do is, if I was doing Lab 10, I would very quickly submit one that returns negative 281 but not look at it. But if you need it on the last day that it's due, you don't want to use up the submission on the last day it's due to get the help page. So I would do it, just scroll through to see that the help is there, and don't really read it carefully. Try to think about the Lab 10 DP. Come to office hours with problems before you look at the help, because the help is going to tell you everything. But think about what it is that the problem is asking you to do. And the real key to every DP problem, I'm going to give you the recipe for solving DP problems. First part of the recipe is know that it's a DP problem. On the exam, reminds me, on the exam, practice folder, final exam, there's 2 practice exams in there, plus some supplemental problems. I've still got to put the supplemental problems up on Gradescope, but the supplemental statement of the problems is there, the starter files are there. I just have to remember to get Gradescope set up for those supplemental problems. But on the exam, we are very careful. The dynamic programming written problem will say dynamic programming, because we don't want you to have to guess. Dynamic programming is hard enough without having to guess whether this is the DP problem or not. So first thing to do, determine that it is DP solvable. Second thing to do, look at the complexities. Look at the memory complexity, look at the time complexity, and that tells you something about both the memo and the form of the solution. So like if I told you that you were allowed O of n times m memory and you were allowed O of n times m time, then that tells you, I think I need a 2D memo and I'm probably going to have 2 nested loops if I do it bottom up. So those inform you of what things will look like. Now, it's not perfect. For example, Lab 10 is a good counterexample. Lab 10, the memory and the time are linear, but you still need a 2D. It's just that one dimension is fixed. One dimension is fixed in size, 0 through 5, so 6 possible values in one dimension. It still is 2-dimensional, but one size is fixed and will never change. Regardless of how many meals you have, your card can have anywhere from 0 to 5 punches, so one of your dimensions is always size 6. So, but still, know that it's DP. Look at the complexity, both time and memory will inform you something about your memo, something about your structure and your time. Then the real hurdle is understanding this DP problem and seeing how does this thing in the memo relate to these other things in the memo. It will always be other things in the general case. There may be edge cases that only depend on one, but the general case depends on at least two other things. If every case depended on only one other thing, it wouldn't be DP. We'd just write it with a loop. We wouldn't even need a memo. We wouldn't need more than one variable. We might need a loop variable and an answer variable, but we wouldn't need n variables to remember. So if a problem only depends on one subproblem, it's not DP. It doesn't have repeated subproblems. I need the subproblem, but I only need it once. So the real hard part of every DP is understanding how does this thing in the memo relate to other things in the memo. And that takes drawing out some examples, thinking about it logically. Don't stare at the code. The code's not done yet. Look, and don't just look at the problem. Draw it out. Like, hey, if I was solving this, I would need a memo. It'd be a 2D memo, and this thing in the memo would be related to these two other things. That's what binomial coefficients is doing. This thing in the memo is related to two other things who are related to other things who are related to either two other things or maybe one other thing plus a base case or whatever. But the general case is related to multiple other things. And once you see that relationship of this one is related to these, then you can write the relationship. And if you can write the relationship, you can write the code. So that's my quick how to solve DPs. All right, so what we're going to do when we do dynamic programming top down, it says we're going to save known values as they are calculated. And this one, it says it's preferred. It really depends on the person and the problem. Some problems I see the top down first, some I see the bottom up first. Like I said, for the problems that we would give you on the lab or the exam, it's going to be solvable either way. Do the one that you're most comfortable with. Now, like I said, the nice thing about the top-down approach is sometimes it's easier to see. If you can write the relationship, you can write the top-down code. You may not be super comfortable with recursion, but more practice will get you there. So if you can write that equation of this thing is related to these two other things, hey, if you can write a recursive definition, you can write a recursive function, and then you can retrofit it to DP. You can make the memo, check if the value is known. If it is, return it. Compute as normal, store it and return it. So you basically, if you can write that relationship, that's the bulk of it, that's the middle part. Then you can create the memo, you can check if it's in the memo, you can save the memo and return. The nice thing also about this is you don't have to worry. Like with the bottom-up coefficient, I had to worry about which loop had to come first. Is it M I'm computing first or N? Which one has to be the outer loop? Top-down takes care of that. Don't have to worry about it. So even if you're not as comfortable with recursion as I am, sometimes the top-down will still be easier because there's less details that you have to worry about. And the other nice thing about top-down is that if you don't need to compute all values, the top-down takes care of that for you. It only computes what it needs. Oh wow, it's like the top-down is like the Liberty Mutual of dynamic programming. You only pay for what you need. Sorry, I don't mean to like silly companies, but I've seen the commercial too many times lately. Okay, so the bottom-up approach is let's pre-compute the values from the base up. We know the base values, we get those into the memo, then we can compute from the bottom up and use some loops to do it. And this one is not really adaptive because it does compute all the smaller cases. Whether they're needed or not, they might get computed unless we spend more time deciding which to do. Now, if we give you one on the exam and we say, hey, here's a problem, you can solve it top down or bottom up, we are not looking for the bottom up that only computes what's needed. If you don't notice that some things aren't needed, that's okay. As long as you're still within the bounds of complexity. If you don't do DP and you just go do the recursion without DP, well, you're going to lose a lot of points because you didn't even try. But if you try and you compute a few things that aren't needed, that'll still fit within the bounds of the complexity that we set. We don't set the bounds based on the most efficient bottom-up. We base it on what could be computed, what could be possibly needed. So we don't base it on what's the minimum computation. We don't base it on, well, the top-down would be this complex, therefore the bottom-up must be written to be the same complexity. No, we give you the complexity for either one of them. Okay, so we can do, at least for the problems we will give you. For the problems we will give you, bottom-up can be used anywhere, top-down can be used. Now, like I said, there are a few problems, complex problems where it's hard to see how to build it bottom-up, and it's much, significantly easier to code top-down, or even impossible to code bottom-up. But for anything that we will give you to solve, if you can solve it, if it can be solved one way, it can be solved the other way. One thing that we have to be careful of is that the memo space has to be sufficient. If the memo would be exponential, then we can't afford the memo. So there are problems that have repeated subproblems, but there are so many repeated subproblems that we can't do DP. And we won't give you one like that. For instance, when you're working on Project 4, Part C, you might say, hey, I might get to a place where the unvisited is like 8, 3, 2, 1, 5, 17. Well, but the unvisited also might be 2, 8, 17, 3, 5, 1. But those are the same unvisited, right? So you could say, well, why don't I save the MST for this and look it up in the future? Well, there's just too darn many of them. You can't afford that much memory. You can't afford the exponential or factorial. Let's say probably exponential or factorial. It's one of the two. Exponential or factorial number of subproblems of combinations of unvisited, let alone indexing them uniquely to so that no matter what order you're given, you look them up and find the one unique way to do it. But there would be just way too many of them to store them all. So some problems, even though they seem like it's recomputing things, and it is, the space is just prohibitive. So we've got to do something else in that case. So we must have enough memory for either approach to be doable before we have to do it. And the top-down could have extra space due to the recursion, but it won't be, remember, it only computes one branch at a time. So because it's only computing one branch at a time, the depth of recursion would be the complexity, and that would just be like adding a +1 to the memo size. So it doesn't change the complexity class if we do top-down. It doesn't change the memory complexity class. It just increases the constant times one of them. Now, the bottom-up approach can recycle and collapse previous steps. It is possible sometimes in bottom-up to use less memory. And we're going to do an example of that in just a second. Top-down can't do that because top-down, you don't know what the order of computation is going to be. You can't say, hey, I'm done with this set of values, I'm never going to use it again. Top-down, you can't predict that. Bottom-up, you sometimes can. Okay, so, it looks like Professor Darden, when he edited these slides, he looked up the answer to the ones that can't be solved. I didn't realize that slide was in there. I know most of these slides really well. I just didn't realize this one had been added. So thank you. That'll save me looking it up and students' time looking it up. So for what we do, you can do either one. But if you want to look up what is a type of problem that couldn't be solved with bottom-up, go look at that. But it's not going to be on the exam. So we've got our summary here about the dynamic programming itself is an advanced technique. It is something that noticing it can save you a lot of time. I wrote a program when I was a PhD student, and I started running it, and it just seemed like it was taking forever. And my first version of the program took 2 weeks to run. I mean, it was running continuously for 2 weeks before it gave me an answer. And then I realized I hadn't saved values that I could have. So dynamic programming reduced it from over 2 weeks to 2 days. So, okay, that's an order of magnitude. That was nice. And then it took me about 3 months to come up with a completely different approach, solves a slightly different problem, but it ran in 30 seconds. So I changed the question a little bit, which allowed me to change the solution completely and changed it from 2 days to 30 seconds. And it's actually a bigger question that gets solved faster, but it's a slightly different question. But the first step of noticing that DP could be working reduced it by an order of magnitude. And Lab 10, if you can figure out the relationship in Lab 10, you can write it without DP, but it won't finish on the autograder in time because we created big enough inputs that the recursive approach would run out of time. So this is an advanced technique that we're going to choose to trade space when there's enough of it to save time. And usually if it's possible, it's a great trade-off. We're trading like linear or quadratic memory to change from like exponential or factorial down to polynomial time. So yeah, a lot of the time, as long as n is anything reasonable, I'm willing to give up n squared memory to go from exponential time down to quadratic. I'll take that deal almost any day. But we just have to look at it and say, hey, how big could this problem be? Is it still reasonable? Is there still enough memory to solve this in DP approach? And we have to have dependent subproblems. We have to have those repeated subproblems where looking them up more than once is what's going to save me time. And then we can write them. Anything we ask you to do can be written top down. It can be written bottom up. Now, what we've got here is another example of DP with something called knight moves. So the other day we did n queens. So this one we're going to look at how a knight moves. So the knight moves in an L shape. It moves 2 spaces in any direction, turns 90 degrees, and moves 1 space. You could also say, well, isn't that equivalent to saying it moves 1 space, turns 90 degrees, and moves 2 spaces? Yes, it is. But the important thing is that from any given starting position, there are at most 8 other places that it could reach. If I started with my K here, well, then I could end up here or here. So if I start in a corner, there's only 2 other places. If I had started here, then there would be 1, 2, 3, 4 other places that it could go. So the number of places could be from anywhere from 2 to 8. It depends on your starting position, but it's never more than 8 other places that you can reach. Okay, so that's how a knight moves. What we'd like to know is, how can I move from one corner to the opposite corner, such as top left to bottom right, in a given number of moves? So we're telling you up front here that if we gave you a size 8x8 board, it can be done in 6 moves. What we want you to answer, so we're going to tell you that up front. We're going to tell you the size of the board. We're going to tell you the number of moves. What you have to tell us is how many different ways could it be done. To answer this, we're going to use dynamic programming. And we're going to basically compute the number of routes to all possible locations after 6 moves. And then when we look at the bottom right, we'll know the answer. Now, here's why DP is important. So we say, hey, here's where I could reach after 1 move. So let's go to the base cases. Base case, 0 moves. After 0 moves, there's 1 place I can be there. All right, so after 0 moves, I can be there. After 1 move, I could be at either of these 2. Now, after either of those 2, so then basically we took the starting one in red, then we got where it can go in black. Then when we move to the next one, this is going to be important on future slides, when we move to the next board, we're saying, hey, the gray ones are the previous move and the black ones are the current move. So gray is where I got to previously, black is where I could get to after 2 moves, and it shows, hey, I could have gotten here or here after 1 move, but either of those could have contributed 1 way to get here. This box, there's 2 ways to get there. There's 2 ways to get there. There's 1 way to get to every other one, except this one has 2 ways also. So that one, instead of numbers, we put 2 knights in there. But in future ones, we're not going to be able to do that. It's going to get too crowded if we do that. So we'll just start putting numbers. So we'll put gray numbers is how many ways to get to the previous locations. Black numbers, how many ways to get to the current locations. So there are overlapping subproblems here because there are 2 different ways, 2 different move ones that lead to the same location after 2 moves. And so I don't want to have to compute each of those twice. All right, so here's memo 0. Memo 0 has, and we're not showing all the zeros, we're just showing the things that are non-zero. So memo 0 has 1 possible way to get to the upper left. And here we're giving you a 5 by 5. When we go up to a full 8 by 8, we're only going to be able to fit 1 board on the screen at a time. So that's why we're getting used to the gray numbers, is we're not going to be able to show you 2 boards at a time when we do an 8 by 8. So here we've got the upper left section, 5 by 5, or it says here it could be the upper left 5 by 5 of a full board. So after 1 move, or after 0 moves, we have 1 place. After 1 move, we have 2 places. And then here's the memo 2 with memo 1 in gray. So that's where we could be after 2 moves. So then let's look at memo 3. Okay, so that's just memo 2 by itself. Memo 3 is, and now we've used multiple colors here, we've got the one possible memo 3 calculated. We've got the purple, I believe, memo 2s are the important ones. They're the ones we're using. The gray memo 2s are the ones that aren't important for this particular location. So when we're calculating this one, we're saying, hey, there's 8 ways to get here after 3 moves. Each of the purple numbers contributes its number to the total. So if there were 2 ways to get here, then that contributes 2 of the possible ways to get there. So that one contributed 2 ways to get there. So this one contributed 2 ways. The one in the upper right contributed 1 way to get there. This one contributed 1. This one contributed 2 ways to get there. Contributed 1, contributed 1. There's 8 ways to get there. And that's just one of the memo 3 squares. If we compute a different memo 3 square, that one uses some of the same ones. Notice both of the 2s are necessary for both of these. Some of the 1s are, it looks like all the 1s are different. It looks like all the 1s are different, but both of the 2s were reused. So both of those 2s got reused for both of these 3s. So the memo sub 3. So memo sub 3, that 8 needed both of the same 2s that the other 8 needed. It used different ones, but it used the same 2s, and we don't want to compute those 2s multiple times. So that's 2 of the memo 3 locations and how they got computed. Here's all of the memo 3 locations with the memo 2s in gray. So that's all of the possible places we can reach after 3 moves. Here's memo 4 only. So if we take that one and compute everything from that, here's all the other things that can be computed after memo 4. Here's memo 5. And notice we're getting some big values in the middle now. And here's memo 6. Now 108 is really the only thing we need in memo 6, but a simple bottom-up approach would have computed everything in memo 6. Top-down approach would only compute this one. It would be the only one it needed from memo 6. It would say, hey, I need this from memo 6. It's the only thing I need from memo 6. Let's see what I need from memo 5. I don't need everything from memo 5. I just need these 2. Those are the only things that I really need in Memo 5. So a top-down approach would have only computed some of Memo 5 and more of Memo 4, more of Memo 3. The further back you go, the more of it's needed for all future things. But when we're near the end, only some of them are needed. Okay, so that's what the memo looks like at every step of the way. So these are the number of ways to reach that location after this number of moves, after 6 moves. Now, here's a couple of questions. So what I want you to do is think about, we're going to go through the questions. I want you to think about them for a few minutes, then we're going to come back and talk about the answers. So what's the time complexity? So that time complexity would be based on, hey, it's an 8x8 board with 6 moves. Well, what about if the board size is n, and when I say n, I mean n by n. So if we say, hey, in general, if I had a chessboard of size n by n, and we had m moves, what would be the complexity in time? Okay, so what's the time complexity for this in general? What's the memory complexity for it in general? How could we reduce the memory? And reducing the memory, remember, only applies to bottom up when you think about it. So think about bottom up. How could we reduce the memory? And I talked a little bit about the top down, so I sort of gave part of that one away. So think about the top down approach. So take a few minutes, think about these. I'll turn off my mic for a few minutes and we'll come back and discuss them. And you can also feel free to discuss these in the chat window with other students. Okay, so the complexity for this solution, well, I did an 8x8 board. I computed it 6 times. Seems like 8 times 8 times 6, right? Almost. So it's 8 times 8 times 6 over 2. Because I didn't compute every value in every board. I computed half the values in every board. All right, what about if it was n size and m moves? Well, then it would be n times m over 2. And the 2 doesn't really matter, right? It's O of n squared m either way. Whether we put the divide by 2 in there or not, it's still n squared times m. Okay, what about the memory complexity? Well, the memory complexity is the same, and it's a real n squared times m. We can't leave half of it off. We can't say, ooh, let's make one without every other square. That would be, maybe we could, but it'd be painful to code it. But memory complexity would be the same, n squared over m. So with the bottom up, how could we reduce the memory? Well, let's take a step back. When I computed fib of 6, and this is bottom up only, when I computed fib of 6, I computed it from fib of 5. If we go back to when we used to have the gray numbers in here, when I computed memo 3, I only needed memo 2. I didn't need memo 1 or memo 0 any longer. So we could do n squared times 2. Basically, I could have the odd board and the even board, and I could either swap them or I could swap my current index. Like I'm computing board, or I could do it modulo, right? I could do it modulo. I could say I'm computing board I modulo 2 in terms of I minus 1 modulo 2, right? So I compute, like when I'm computing memo 6, I'm really computing board 0 and I'm computing it in terms of board 1. So we could have really 2 boards. Well, actually, we could get it down to n squared. If we notice that we only use white squares or gray squares in each one. So I could say, well, I've got one board. I compute the gray squares in terms of white, then I compute white squares in terms of gray, then I compute gray in terms of white. And if I'm careful about it, I don't even have to re-zero them. I just set each one to 0 as I calculate all 8 that could contribute to it. So I say, hey, before I compute this one, let's set it to 0, and then let's sum up the people that add to it. So I would just zero out each value as I compute it. I could get this down to n squared memory. Would I necessarily choose to write it that way? Maybe not. I might stop at this one and say, hey, I did the bottom up and I only needed 2 boards, not m plus 1 boards, right? So in 6 moves, I really needed 0 through 6. So I didn't really need m plus 1 boards. I only really needed 2. I probably wouldn't go with this far if I was writing the bottom up. But with the top down, you can't cut out the memory, because the top down is going to go out through a path where it goes through this one in terms of 6 moves, that one in terms of 5, these in terms of 4, this one in terms of 3, and it'll go down to the zeros and then back up, down, up, down, up, down, up, down, and it'll do all kinds of things. So with the top down, you can't cut down the memory. You have to leave it as the n squared m. Okay, and like I said, the top-down method, basically the top-down method would say, make the memo, call the helper, and return it. So I call the helper, I'm saying, hey, it's a 8x8 board with 6 moves. I want to know how to get to this position after 6 moves. And then that one would have to say, well, to get to this one after 6 moves, I would need, well, where else could I get to? Of all the 8 possible places, 6 of them are off the edge, but I would need this one after 5 moves and this one after 5 moves. And then each of those would say, well, I go through all the possible 8 things that I would have to do, and anything that's not off the board, I need that one, and I call it recursively. And every recursive call would say, if the value in the memo, if the number of moves is 0 or the value in the memo is greater than 0, I return it. Otherwise, I calculate it, store it, and return it. So we don't actually have code written for this one. So it wouldn't be a bad one to write. It would be a little bit complicated in terms of is this other location going to be off the edge or not? So and you could have, like, basically everywhere you've got to make a move, there's going to be like 8 if statements. Like, if this thing is not off the edge, then calculate the contribution of this one. If this thing's not off the edge, calculate its contribution, etc. So that's part of why we didn't write a solution to this one, is it takes like these 8 ifs for every possible location. Like we said, it's n squared times m. It's really n squared times m times 8, but that's just a constant. But everything you compute has 8 possible other things that you have to say, well, if that other one isn't off the edge, then it contributes to this one. Okay, so that's the end of the slides. Okay, I thought excuse me, got done just like, hey, a minute early today. Awesome. So start thinking about DP, start thinking about Lab 10. Don't leave Lab 10 for like, hey, I'm going to do Lab 10 in like 15 minutes. The Lab 10 autograder takes some thinking. So start thinking about it. Come to office hours, prof hours with questions. Get the submission in. That'll give you the help page. Just don't look at it first. Try to solve it yourself. Come to us with questions. Look at the help page if you need it and you're running out of time. But you'll get more out of the Lab 10 AutoGrader DP meal plan program if you think about it first, because I can almost guarantee you we're going to have a DP problem on the final. We've had a DP problem on the final every semester for as long as I can recall. So chances are really high there's going to be a DP problem on the final. The way you get better at them is by doing them, and Lab 10 is a good chance. Okay, let's call this done, get some lunch, and we'll see you at Prof's Hours.